Okay, can I start?
You can start.
Okay, thank you, Mark. So, first of all, I would like to thank Mark and all the organizers for the opportunity to give this seminar to this amazing community. So, during this seminar, I will talk about the work Asymptotic Safety in Generalized Proca Theories that I've done with Lavinia Eisenberg and Alessia Platania. Basically, in this work, we investigated if generalized Proca theories admit an ultraviolet completion within the quantum field theory framework. And so, in order to start, okay, let's talk about generalized Proca theories. So, as the name suggests, generalized Proca theories represent a generalization of the Proca theory, meaning the massive vector field Lagrangian. In order to get generalized Proca theories, we start from flat spacetime and we add to the Proca Lagrangian higher derivative self-interaction terms in the vector field in order to get the most general Lagrangian, which leads to second-order equations of motion. But it's not only that, because we also require that the longitudinal mode is a Galilean. And in a few moments, I'm going to tell you what a Galilean theory is. Now, regarding the motivations behind the formulation of these theories, in order to understand the rich phenomenology that these theories have, we need to pass from flat spacetime to curved spacetime, because in the latter case, we will have non-minimal couplings between the gravitational field and the vector field. And in particular in cosmology, these theories admit an isotropic and homogeneous cosmological solution that drive the cosmic acceleration without a cosmological constant. So they are good candidates for describing dynamical dark energy. Due to the presence of all the non-minimal interactions between the gravitational field and the vector field, these theories there are a lot of interaction couplings, of course, in these theories. And these couplings are partially constrained by data and effective field theories. Now, in order to see how we can construct these theories, let's start with Galilean theory. The Galilean theory is a generalization of the scalar field theory in flat spacetime, and we can obtain this theory starting from the scalar field Lagrangian, considering higher order derivatives in the scalar field, requiring second-order equations of motion and Galilean and shift invariance. Now, this theory was introduced in order to describe dynamical dark energy. It was one of the attempts in order to describe dynamical dark energy. And actually, they worked quite well, unless for the fact that a fifth force arises with this theory. And in particular, there are non-screening mechanisms for this fifth force. And so they are not compatible with the experimental data, the observations. But with these requirements, let me go back to the requirements in order to construct Galilean theory, we end up with this Lagrangian, where, as you can see, higher order derivatives appear in the scalar field, and there's this peculiar form in order to obtain one propagating degree of freedom. Now, in order to maintain this structure of the Galilean theory, introducing also a screening mechanism of this fifth force in order to get a good description for dynamical dark energy compared to our data, our observations, generalized Proca theories were introduced. So, as I mentioned before, we had higher derivatives in the vector field, requiring 3 propagating degrees of freedom, and the longitudinal mode must be a Galilean. So, with these requirements, we end up with this Lagrangian, where not only the kinetic term for the vector field, but also all these other terms appear here, where the mass term is contained in this L2, where the px corresponds to the order in the vector field for each term appearing in the Lagrangian here. So for L2, there's not only the mass term, but also other terms quadratic in the vector field. And also here, all these coefficients appearing in the Lagrangian are functions in the vector field, in particular in the squared vector field. Okay, so this is in flat spacetime. Now, we're interested in what happens in curved spacetime. And in order to pass from flat spacetime to curved spacetime, not only we have to replace partial derivatives with covariant ones, but in order to fulfill all the requirements for generalized Proca theories, we also need to add non-minimal couplings. And in particular, with this construction, the longitudinal mode satisfies the is characterized by the Ordesky-like interactions. So, with this construction, as you can see here, the Lagrangian of generalized Proca theories in curved spacetime, still the kinetic term appears, but also all these other terms. Some of them are similar to the others that I showed you before, this one for flat spacetime, just replacing the partial derivative with covariant ones, but also non-minimal interactions appear in between the gravitational field and the vector field. Still, there are general function appears quadratic in the vector field, and as you can see, there is this peculiar form in the Lagrangian due to the requirements of free propagating degrees of freedom for the vector field. And so, this is the general Lagrangian. As you might see, there are interaction couplings. Sorry, is there a question? No? Okay. Yes, please.
Yes, hello. I'd like to ask probably a stupid question, but anyway, this theory seemed to contain higher derivatives. What about unitarity? Is it unitary, or what can we say about that? Or at this point, we don't care.
Actually, there is a work by Claudia de Ram and other people where they found positivity bound, they found constraints in order to require the unitarity for these theories. So there are.
What are these constraints on? Is it like these form factors or what?
Actually, it's about the couplings, but you can see more about that in the. I'm gonna quote this work later. So if you wanna, you can go more in depth about that, about unitarity, causality, and so on, with the work of Claudia and Lavinia, and I don't remember the other authors actually, but I'm gonna show you the reference.
Okay, thank you.
Thank you for the question, actually. So, okay. So, as I was saying, there are a lot of couplings here appearing, interaction couplings, and in particular, I mentioned before that they are partially constrained by data and positivity bounds. But what about constraints from fundamental physics? I mean, these theories are unconstrained in some ways, and they are highly special due to the requirements in order to get generalized Proca theories. So we wondered if these theories are compatible with fundamental physics. Can these theories be constrained by fundamental physics? And that's the problem we want to tackle. So since it's not clear whether generalized Proca theories are fundamental and they lack constraint at a fundamental level, we want to investigate first if these theories admit an ultraviolet completion, and that's actually what we've done in this work. I'm going to talk about you. And then we want to study the asymptotic safety landscape coming from the fixed point, and this is for future work. So actually the idea is the following, and it's well depicted in this image taken by the work of Benjamin and Alessia. Here, as you can see, it's analog to what happens in string theory as asymptotically safe gravity. So we first of all investigate if an ultraviolet completion exists. So here. Then we study the flow, we study the asymptotic safety landscape emerging from the ultraviolet completion, so from high energy limit to lower energies here. And once obtained the landscape emerging from the ultraviolet completion, then we are able to compare it, for example, here with positivity bounds. In our case, for our future work, we need to study the asymptotic safety landscape to get the asymptotic safety landscape in order to compare it with positivity bounds and all the cosmological data. Okay? So if these theories are compatible with fundamental physics. So in order to start our work, we chose these ansatz for the Lagrangian, which is up to the fourth order in the vector field and up to two derivatives. And in a few moments, I'm going to tell you why we chose these ansatz. But notice that here, there is the first term that breaks the U1 gauge symmetry, because G2 is related to the mass of the vector field. And also, as in most of FRG computations, we use the Euclidean signature. So, before telling you why we chose these ansatz and also the setup that we chose for our computations, let me stress the peculiarities of these theories. Now, as you can see here from the Lagrangian, this Lagrangian is highly special because it's constructed requiring that there are free propagating degrees of freedom. Now, for constructing this Lagrangian, there are no symmetries required in order that protect also this structure, which means that the renormalization group flow could generate terms that break these structures. Okay, that's one problem regarding the non-triviality of the RG flow for these theories. Another problem is that due to the construction, due to the requirements for generalized Proca theories, as you can see, there are some interaction couplings multiplied by different operators, for example, for these square brackets. Now, typically, different operators run independently. But if we multiply different operators, for example, this one, we multiply them by different couplings, we break the structure of generalized Proca theories. We're out of Proca's domain. And so, for these reasons, the formulation of the RG flow that keeps the Proca structure is non-trivial. So, it's not obvious that these theories can accommodate an ultraviolet completion. So, taking in mind these warnings, we chose these ansatz in order to get a minimal setup to compare with positivity bounds for future work. And this is the work that I was mentioning before, where they got the positivity bounds for these theories. And so the minimal setup requires fourth order in the vector field and two derivatives. But we chose our setup in order to stay within the Proca domain, but minimizing also the difficulties of our computation. And in order to do that, we first of all use the background field method, which means that we linearly splitted each field in the background field plus fluctuation field. In order to get a closed form of the vectoric equation, we performed the background field approximation, and we chose as background field for the gravitational sector an Einstein manifold, while for the vector field, we chose as background the constant vector field. Last but not least, in order to simplify the calculations, we chose for the gravitational sector the harmonic gauge condition. Now, since we chose these backgrounds for both fields, at the end, starting from our ansatz, we end up studying the Lagrangian with only 6 couplings because we are not able with this choice of background field to extract the flow of all the couplings, only multiplying operators with derivatives in the vector field, so for these couplings and this one. Now, with this choice, each interaction coupling here multiplies only one operator. Then this choice is still consistent with the Proca domain, with the generalized Proca theories formulation up to the fourth order in the vector field. Not only that, also here, as you can see, there are other underlying terms characterized by derivatives in the vector field, but they, even if there are derivatives in the vector field, will still contribute in the computation when we compute actually the regularized two-point function. Okay, so they will still contribute. Now, before moving on to the computation of the FRG flow, let me stress one thing regarding, in general, the Proca theory. So, in the Proca theories, the longitudinal mode is physical because the U1 gauge symmetry is broken due to the presence of the mass term plus, in this case, other terms. Okay? And so, no gauge fixing is needed in this case, but the longitudinal mode is still static, as written here, in the sense that if we look at the longitudinal propagator, meaning the propagator of the longitudinal mode, there are no contributions coming from the kinetic term. which means that the Wilsonian shell-by-shell regularization for this mode, for this physical mode, will be ineffective. However, in order to treat all the physical modes in the same way and to avoid spurious scheme dependencies, not only that, also to simplify our calculations, we regularize it in the same way as the transverse mode, okay? So with this in mind and with all this setup, we computed the FRG flow. Now, as usual, the left-hand side of the vectoric equation took half a second, so it was a piece of cake in this sense. But the right-hand side was quite involving, and now I'm going to show you step by step what we have done. So, first of all, we computed the regularized two-point function. We easily computed it, so nothing special. But the most involved step was the inversion of the regularized two-point function, and now I'm going to show you why. In order to compute the regularized propagator, we used the Parker-Fulling expansion. So the idea was to treat the full inverse propagator as a differential operator characterized by a simple solvable piece, for example, the kinetic term in our field, plus all the interaction terms, background corrections, and so on. In order to compute the propagator, so we perform the expansion, which is a geometric series that should match the truncation order of the effective action. So we will keep only the terms compatible with our truncation in the effective action. Now, in our case, we have two fields non-minimally interacting with each individual propagator. Now, we had to compute this multiplication between the propagator and the derivative of the regulator. So, first of all, we had to invert this matrix, which means to compute each element appearing in this matrix. Now, we won't care of the non-diagonal term because once multiplied these two matrices, we will only be interested in the diagonal elements of this matrix. So the aim is to compute these two elements, okay, where di is each individual propagator occurring in our analysis. And so, in order to do that, we applied the Parker-Fulling expansion first to each individual propagator here, di, okay? And the expansion, so is with respect to vi, the interaction. Then we use this Parker-Fulling expansion to all the diagonal elements, for example, this one, but it's equivalent for the other diagonal element, of course. And the hardest part of this work was at a computational level, because, I mean, the formula is this one, and as you can see, it's quite long. The right-hand side is given by 5 lines, but it's not the problem of the Parker-Fulling expansion itself, but the problem arises with the truncation order that we considered, because we are considering a truncation order which is up to the 4th order in the vector field and up to 2 derivatives, which means that here, in each term, there are going to be, in the interaction part, other terms. Each term will be up to the 4th order in the vector field. So a lot of terms are involved, which means that this step was hard at a computational level, okay? But at the end, we figured out how we manage it, and so we successfully computed the Parker-Fulling expansion. But it's not the end of the story, because each term generated by the Parker-Fulling expansion is characterized by Laplacians, open derivatives, tensors, and so we couldn't apply the standard it-kernel techniques to this term, in principle, with the terms obtained by the Parker-Fulling expansion, because before that, we had to recast each term in order to apply the usual it-kernel techniques, iteratively using the commutation relations derived by Benjamin in this paper. That's because actually we can apply the usual it-kernel techniques only when the Laplacian functions are in between tensors appearing on the left and open derivatives appearing on the right. So, in general, if we have a general function of the background Laplacian, WV, which is an arbitrary operator, and X, a tensor of arbitrary rank, then in order to get a suitable form for applying the usual it-kernel techniques, we need this f of the Laplacian, this function, in between W and X. But moving f, of course, it's not the end of the story because we need to take into account the commutation relation between W and the function of the Laplacian. Now, in our case, we needed the commutation relation in the case of WV as a multiplication operator in the sense given by Benjamin in his paper. In this case, the commutation relation is given by this right-hand side that replaced in this general expression leads to the final formula that we iteratively replaced to each term got by the Parker-Fulling expansion in order to get a suitable form for each term for applying the usual it-kernel techniques. Now, notice that, of course, we need to be consistent with our truncation order, which means that since we are looking at a truncation up to the fourth order in the vector field, up in two derivatives, we didn't have to take into account so many terms appearing here on the right-hand side of the final expression in the commutation relation, because as you can see here, the Laplacian of the nth order appears. So there were a bunch of terms, few terms, but in order to be consistent, of course, with our computation, we had to take into account the commutation relations, okay, in order to easily apply the usual it-kernel techniques. Ooh la la. And so, once applied the commutation relation, we used it-kernel techniques in order to evaluate the supertrace, and at this moment, so we are able to compare the right-hand side with the left-hand side of the vectoric equation in order to extract the beta functions. Now, looking at the fixed point equations, this system of fixed point equations is highly nonlinear, which means that in principle we would have many fixed point solutions. But we expected that not all of them are actual fixed point solutions because we're studying a truncated dynamics. And so there are going to be spurious solutions due to the truncation that we are analyzing. So in order to track the actual fixed point solutions, we perform the analysis starting from the Einstein-Hilbert truncation and solving for this first truncation the fixed point equations and getting the critical exponents. Then we added one coupling at a time, and when necessary, I'm going to show you when, we slowly activated the new added coupling. And with the new truncation, we solved fixed point equations looking at the continuation of the fixed point obtained previously. And we did it up to the maximal truncation considered. In order to track the evolution of the fixed point across the truncations, we looked at the fixed point coordinates and also at the critical exponents. So that's how we performed our analysis in order to avoid the spurious solutions. Okay? So let's move on to the results. So as I mentioned before, the first step was given by the Einstein-Hilbert truncation. And for this truncation, we got the Reuter fixed point solution. Fine. The second step was obtained by adding to the Lagrangian what is the mass term of the vector field, which means that we considered as second step the Lagrangian given by the Einstein-Hilbert part plus the Proca Lagrangian minimally coupled to the gravitational field. And at this step, we got the continuation of the Reuter fixed point plus two spurious solutions. Spurious because they disappeared starting from the next step, and they disappeared in the sense that each of them became, starting from the next step, a complex conjugate pair. That's why they disappeared. So in this table, I show you our results for the first and second steps. So for the Einstein-Hilbert truncation, we found the Reuter fixed point characterized by these fixed point coordinates. And here there are the usual pair of complex conjugates for the critical exponents of the Reuter fixed point. Then for the second step, as you can see, taking into account only 4 significant digits, the fixed point coordinates for lambda star and G star are equivalent in between these two steps, while for G2 star, the dimensionless coupling related to the mass of the vector field, is 0. And here, as you can see, also the critical exponent, 2 of them are equivalent to the ones obtained previously for the Reuter fixed point. Then we have also the other critical exponent here. And in the other 2 rows here, you can see the other 2 fixed point solutions that we obtained, but actually, starting from the next step, they disappeared because each of them become a complex conjugate pair. Okay. Now, for the third step, in order to get the third step, we added the first non-minimal coupling to the Lagrangian. And for this truncation, the fixed point structure drastically changed. First of all, the Reuter fixed point disappeared. But here there's a caveat, and I'm gonna talk about this later. It disappeared, and instead of that, we found at this step 3 fixed point solutions which appeared at this step, but they remained across the truncations starting from this step. And actually, due to their behavior, looking at their behavior, we called these 3 fixed point solutions the Proca triplet. In order to understand why the fixed point structure drastically changed from the second to the third step, we slowly activated this non-minimal coupling, the first non-minimal coupling added to the Lagrangian, which means that, as you might see from this plot, we started from the red point, which is the Reuter fixed point at the second step when G41 was equal to 0, and then slowly activating G41, so the first non-minimal coupling, the new added coupling, slowly activating it for positive values, then we have to follow this green line going to the yellow color, and we end up with this empty blue dot, which is one of the fixed point solutions at the third step. On the other hand, slowly activating G41 for negative values, we can go either end up with this filled blue dot, okay, and for still negative but smaller values of G41, following this line, this blue line, we end up with this filled blue dot. So these blue dots represent what we call the Proca triplet, the 3 fixed point solutions that appear at the first step, and they remained across all the truncations. And I'm going to show you now in a moment. Now, these 3 fixed point solutions were classified by us according to their behavior across the truncations, but also comparing one to the other, looking at the fixed point coordinates and also their critical exponents. Indeed, we call the main Proca fixed point the only fixed point characterized by non-tachyonic mass across all the truncations. And here, this main Proca fixed point is given by this empty dot because it's given by a complex pair at this step. And in a few moments, I'm going to better specify it. Then we have the other filled blue dots, which are real fixed point solutions that we call the twin Proca fixed points because they are characterized by tachyonic masses. In particular, the identical twin Proca fixed point, which is given by this blue dot at this step, is similar to the main Proca fixed point looking at both the fixed point coordinates and the critical exponents, while the accidental twin Proca fixed point that at this step is given by this blue dot here in the corner is very different to the main Proca fixed point at the beginning, but then across the truncations it becomes similar only looking at the fixed point coordinates. Now, you could say now, well, you're talking about similarities, differences, comparing a complex conjugate pair given by the main Proca fixed point. You're talking about non-tachyonic mass when we have a complex number for the tachyonic mass, and you're comparing these complex numbers with two real fixed point solutions. Well, because the main Proca fixed point only at this step is given by a complex conjugate pair, because starting from the next step, it becomes real, and I'm going to show you in a moment how we determine the change of behavior of the main Proca fixed point from the third to the fourth step. And so when I talk about similarities and differences in between these elements of the Proca triplet, I'm referring to what happens starting from the next step when the main Proca fixed point becomes real. And in order to see this, we slowly activated the new added coupling, which is G4, in order to understand what happened to this complex conjugate pair. And indeed, as you can see from this plot, all the imaginary parts of the elements of the complex conjugate pair, which are different from zero at the third step, become zero once added the new added coupling G4. So as you can see, the two elements of the complex conjugate pair collapse into a real fixed point from the third step to the fourth step. And so the main Proca fixed point becomes real at the fourth step, and it remains real up to the final to the maximal truncation that we considered. And so here in this plot, I show you the evolution of each element of the Proca triplet across the truncation, starting from the third step when these fixed points first appeared. Okay, so as you can see here, the accidental twin Proca becomes similar to the others, looking at the fixed point coordinates, only at the final stage. At the beginning, it's quite different. And in particular, here we depicted with these empty circles, actually the main Proca fixed point at the first step, because it was given by a complex conjugate pair. So here we're taking into account only the real part of the complex number that describes the main Proca fixed point at the third step, okay? And now let's discuss a little bit about the behavior of the fixed point evolution across the truncations. Because as the name would suggest, we called this solution main Proca fixed point because we found it as the best candidate for an ultraviolet completion for generalized Proca theories. Because it's characterized at the end, starting from the fourth step when it's real up to the final stage, it's characterized by a non-tachyonic mass. Now, since at the beginning, when it appeared for the first time, it's given by a complex conjugate pair, this behavior, the fixed point evolution of the main Proca fixed point across the truncation, is characterized by a slow convergence. This slow convergence across the truncations could be either related to the fact that we need more operators and higher order truncation in order to see a faster convergence across the truncations for the fixed point evolution, or maybe these theories do not admit an ultraviolet completion. So maybe that's a problem related to this behavior, this evolution. But looking at the main Proca fixed point as best candidate for ultraviolet completion for generalized Proca theories, at the final stage, so looking at the full truncation, the maximal truncation, this main Proca fixed point is characterized by 5 relevant directions out of 6, which means it's less predictive compared to the Reuter fixed point. And in order to talk about this, about the relevant directions, so looking at also the critical exponents of the main Proca fixed point, here in these plots, I show you the evolution of the real part and imaginary part of the critical exponents of the main Proca fixed point across the truncation, still starting from the step when the main Proca fixed point first appears. Now, as you can see, First of all, here also the evolution of the critical exponents is characterized by a slower convergence. So still, either it could be related to the fact that we need more terms and higher order truncation in order to see a faster convergence across the truncation, or these theories do not admit an ultraviolet completion. Not only that, also looking at the values of the critical exponents the main Proca fixed point, they are somewhat different with respect to the canonical values of the critical exponents. And so this suggests that we are looking at a highly non-perturbative ultraviolet completion for these theories. Maybe this behavior, the difference between the critical exponents obtained and the canonical values reduces if we consider more terms actually in the maximal truncation. So taking into account more terms and higher order truncation, maybe this difference will reduce. Or the behavior, the difference between our critical exponents and the canonical values is due to a truncation artifact, which means that still maybe this ultraviolet completion does not exist for generalized Proca theories. Okay? So if you're interested in our paper, there are these plots also for the other two elements of the Proca triplet. But this is not the end of the story, because I said before that at the third step, the fixed point structure drastically changed. I showed you how we noticed it slowly activating the new added coupling. But I mentioned that there was a caveat about the absence of the Reuter fixed point. Because actually, if we try to numerically solve the fixed point equations, we still find the Reuter fixed point as solution. In order to be 100% sure about this, we replaced all the couplings of the massless Reuter fixed point in the betas. And we found out that all the betas were divergent, replacing by hand the fixed point coordinates for the massless Reuter fixed point. So, looking at the singularity structure of these betas, we found out that if we send first all the dimensionless couplings to 0 except G2, that I recall you is the dimensionless coupling related to the mass of the vector field. So sending first all the dimensionless coupling to 0 except G2, and then sending G2 to 0, all the betas vanish. Now, why this behavior? Well, if we think about the propagator, the longitudinal propagator, the propagator for the massive vector field in general, the limit of m, the mass of the vector field that goes to 0, corresponds to restoring the U1 gauge symmetry. So within this limit, we are outside of the Proca domain. And so the longitudinal mode from physical becomes unphysical, and it needs a gauge fixing term. We need to restore the gauge fixing term in the Lagrangian for this limit. And so this is reflected in the singularity structure of our betas, because actually the Reuter fixed point can still act as a quasi-fixed point for certain trajectories, the trajectories for which all the dimensionless couplings go to 0 faster compared to G2, which is still related to the mass of the vector field, that should go to 0 slower compared to the other couplings, okay? And similar considerations apply to the shifted Gaussian fixed point line that I'm gonna show you actually right now in this plot. So here in this plot, I'm showing you the projection of the flow in the lambda G41 plane. I recall you G41 is the first non-minimal coupling added to the Lagrangian. And in particular, here, we're considering the flow for the maximal truncation. These symbols refers to each element of the Proca triplet. And in particular, the red line is the shifted Gaussian fixed point line, characterized by all the dimensionless couplings set to 0, except for G41 that can assume any value. In particular, this line acts as both singular line and shifted Gaussian fixed point line, because this line is at the edge of the betas domain due to the fact that all the dimensionless couplings are zero, and so inside all these couplings set to zero, there is also G2. So the same considerations that I've done before apply to this case. In particular, only for some trajectories, this shifted Gaussian fixed point line will act as a quasi-shifted Gaussian fixed point line in particular. Okay? And also here, let me stress that we chose this name, main Proca, identical twin, and accidental twin Proca, for the behavior of these fixed points. Because as you can see here, for example, in this plane, the main Proca is given by the green circle here, and the identical twin, which is given by the orange square, overlaps with the main Proca fixed point. And here you will find the accidental twin Proca fixed point. So they are near to each other, actually, looking at the fixed point coordinates. Okay? So let me go to the conclusions. Generalized Proca theories are characterized by a rich phenomenology in curved spacetime. Indeed, they can give an explanation for the dynamical dark energy. They are actually theoretically and experimentally constrained, but only in the low energy limit. And so we asked ourselves, what about the ultraviolet completion? What about the high energy regime? Can we constrain, so if there is an ultraviolet completion, can we constrain Wilson coefficients from fundamental physics? Are these theories asymptotically safe? In order to tackle this problem, all these questions, we first try to answer the first one, investigated if these theories admit ultraviolet completion. And actually we found a candidate as ultraviolet completion, the main Proca fixed point, which is for the maximal truncation characterized by relevant directions, which means 5 free parameters to constrain, and they are, of course, these theories, so looking at this fixed point, are less predictive compared to the Reuter fixed point. Looking at the fixed point evolution across the truncation, this evolution is characterized by a slower convergence compared to the fixed point of the asymptotic safety scenario for quantum gravity. And is it the slower convergence due to the number of operators, so to the truncation order that we took into account, or is it a truncation artifact? Actually, the only thing that we can say is that standard asymptotic safety is still on much more solid grounds, and in particular, if you are interested in the topic, I will suggest also this paper published by the Heidelberg group here, which came out a few months later compared to our paper, actually, but it's on the same topic. So I will kindly suggest you to read this one also. And so from our results, the next steps will be use the fixed point line to determine Wilson coefficients. So study the asymptotic safety landscape emerging from the fixed point found and constrain the Wilson coefficients for generalized Proca theories, and then compare the infrared behavior that we obtain from fundamental physics with the positivity bounds. And with this, I thank you for the attention.
All right. Thank you very much, Sara, for the nice talk.
Thank you.